Welcome to the CCOM-OE seminar series. Today we're very happy to have Professor John Hughes Clarke presenting for us. He has degrees in geology and oceanography and has spent the last 35 years using active acoustics to investigate modern sedimentary processes in shelf and deep sea environments. He currently works within the UNH Center for Coastal and Ocean Mapping, where he undertakes research and teaching on aspects of multi-beam surveying that are most critical in support of national mapping programs. If you have any questions that you would like to ask during the presentation, you may do so. Otherwise, you can enter your questions into the chat, or we'll wait until the end where you can directly ask your questions. And with that, Professor John Hughes Clarke, you can present and share your screen.
Thank you, Nicole. I'm just going to share computer sound. So hopefully you can all hear me. Thumbs up from Nicole. Perfect. Let me just bring the thing up. So thank you all for listening. Hopefully this environment will change very soon. All of you that are over 16, I hope you're registered if you're in the state of New Hampshire. Nicole and Coral actually brought this up on the weekend because there was unfortunately a cancellation. So it was actually a nice chance for me to tell a story. As you know, I love telling stories. And it's something that came upon me by surprise. And I think a number of you have heard that I like turbidity currents. And this is really an extension of that. I think I've talked a couple of times about the program I've been involved with. But this is something a little bit different. And I'm aware it's a general audience here, the ocean engineers and scientists. So scientists, you're very familiar with turbidity currents, but it's really their monitoring. It's an engineering problem. And it's part of a program. It's actually 3 funding sources. Exxon, who are actually interested in turbidity currents. Kongsberg, who support a lot of this work. They pay for all the field programs. It's actually all done in Canada. And they're interested in the active sonars, but you'll notice we don't need to be active. It took me a decade to realize that. And my day job with CCOM, that there is, as part of the grant, both this and the last one, there is a requirement to understand how well these mapping systems can see seabed change. So turbidity currents change the seabed at great depths. It's a great test of systems. But if I'm going to summarize this in one statement, it's you don't need to stand in front of a moving train to know that it's going fast. And turbidity currents, if you've ever seen one in a flume, they're sweet, gentle looking things, but they are brutal to instrumentation. So that's what I've been sort of working at for the past 17 years. And it is one of the most significant sediment transport processes on the planet, comparable to the fluvial systems, the rivers. And you know, USGS and Geological Survey of Canada, Environment Canada monitor the rivers. We really know so little about what's changing our margins. So you just have to spin up Google Maps, look at our east or west coasts or the Gulf of Alaska, and they're just riddled with these deep sea channels. We learn about it in our marine geology courses, but these processes evolve across the margin. And well, why do we care? It builds our continental margins is the fundamental science question, but why do your typical Joe Blow like it? It damages infrastructure, and sort of deep sea cables were the classic pipelines, deep water hydrocarbon extraction. They are a major concern. And from the oil industry's point of view, they're actually more interested in the fact that they're how deep water reservoirs are formed. And one of the strange things is the latest justification, it's all climate change driven, is that it's a mechanism for exporting carbon into the deep sea. I'm not sure I entirely understand that, but they're important to monitor. And so what is the mechanism? It's not what you see in a lab, as it turns out. And particularly, how does it evolve? You're looking from the shelf break through the slope, the rise, and out onto the abyssal plains, onto the lobes. So Geology 101, we've all heard about the 1929 event, broke 10 cables off a magnitude 7.2 an earthquake. And the cable breaks told us it was moving at 20 meters a second, that's 40 knots. And but the funny thing is that that's not a good way to monitor turbidity currents. That was actually my thesis, looking at the active sonars, imaging the floors of those channels 30-something years ago. But it wasn't till the early 2000s that we started to get good measurements of field scale turbidity currents. Monterey Canyon, USGS, and Mbari were really the first ones. And the oil industry actually are very interested of West Africa. The Congo River and Canyon and fan system, they discovered these amazing currents. And I emphasize the horizontal scale, a turbidity current that goes on for 6 to 7 days. And but the thing is, we need the whole system going from the shelf break canyons through to the abyss. And so far in the deep ocean, we've only measured them in the constrained part. It's like looking at something in a bullet as it goes through the barrel of the rifle, not where it actually ends up, where you get net deposition. So deep sea moorings, it's tricky. You have to put something down in 1 to 4 kilometers of water, and they don't happen a lot. Geologically, they don't happen for 10 or 20,000 years, but in places like the Congo, you might have to wait 3 to 18 months. And when it does come along, it destroys most of your equipment. And this is a real problem. They are not benign objects. They can move at 20 knots, 10 meters a second. And so the programs that have really been implemented in the last 10 years, not one mooring, but a line of moorings, they've had tremendous damage. And it's great reading and they've learned a lot, but when your instrument is dragged 10 kilometers and buried, it's hard. The Congo Canyon, they laid 12, that's the record. And they laid it over 600 kilometers. They were supposed to leave it there for 2 years, but within a few months, most of them have been ripped out by the first big flow. So there is a challenge to instrumenting these. And part of the issue is understanding the turbidity current. There really is gradients in them in concentration, and you have the bottom boundary layer we know from open channel flow, but we've got this upper boundary layer. People have always simplified them as layer average, and it's very convenient, but it misses the fact that they're mainly driven, as we're learning, by dense basal layers. And this is something it's very hard to measure. They're incredibly destructive, but they're carrying most of the momentum. And so we haven't been able to see these except indirectly. As soon as you get grain to grain interaction, it actually supports the flow. And as we're going to find out, it makes a noise. So the classic model, you've got various parameters for a turbidity current. You've got their thicknesses, their excess density, and you've got a slope. And there are simplifying formulas that tell you how fast the head versus the body will go. And for the ones we see in the lab, they're almost entirely, the body is feeding the head. So basically the internal flux is forward inside it. And whether they go is basically how much sediment they can pick up versus how much they lose. And there's this ignition, and it's very much a positive feedback. So unlike a saline flow that accelerates slowly, these accelerate surprisingly fast, and also they can stop very, very rapidly. But what's come out of those mooring programs in the last 10 years is that the flows in the field don't act like that. It turns out the body velocities are actually quite a bit lower than the head. And what they found, particularly in Butte and in Monterey, is it'll start off being a small current and it stretches. And that's how you get seven or 8 days in the Congo. It didn't start like that. So this is the challenge. We want to monitor a flow, not just at one location. That's not good enough. We need to monitor it from inception through the channelized out onto the unchannelized. And of course, as the gradients change, so the velocities will change, we need to multiply that. And the one that nobody's done with moorings is when you lose your confinement, when you go out on the lobe. And from the oil industry point of view, that's where the interest is, because finally you deposit, you get a geological record. So if we're going to monitor these, we can't have one mooring, we need many. And particularly when you get to the lobe, we've got to account for the lateral variability. So it's becoming a real challenge. We want to know about these, they destroy our instruments, and we need lots of instruments. Is there another way? And of course, it's going to be hard in the deep ocean. So I've been working on a very nice proxy. They're the fjords of British Columbia. They're all glacially fed. They're much shallower, but if you happen to look at them, they look just like our continental margins. And the ones I've been working on is the Squamish. I'm just going to be showing you a 6 kilometer section, but in civilized water depths, maximum 230 meters. But you'll see all the variability we have in the deep sea. And particularly, you'll go from a channelized system to an unchannelized system. So now it's shallower, we can experiment with all sorts of different designs. You can still, the challenge is you've got a thin flow that may last no more than 2 or 3 minutes, and you have to wait a month to get it. You can put seabed moorings down, and they work until they don't, until they're buried. But what we've mainly done, because it's shallow, is we actually have anchors out on either side of the channel, surface buoy, and we just suspend the instruments safely above the flow. So they can be, it's like being suspended above an oncoming train. I wouldn't recommend it, but it generally works. And the big ship operation, they are still doing it in Butte Inlet, but it isn't actually necessary. So just the great thing about the Squamish, I should emphasize, is that everything happens really fast. 1 million cubic meters a year arrives. But most importantly, we don't just look at flow in a confined channel. It starts spilling over bank. And most importantly, we can see what's going to build our margin, that the flow in an unconfined sense. And the amount of events, if you get right up against the delta, you'll see 100 events a year. As you get further away, they exponentially drop away. And I used to work close, but what I'm going to show you is the transition as you go out onto the unconstrained flow. And I think I've shown this to people who've heard my story before, but we started off surveying up at the lip, repetitive surveying with a multi-beam. You see the seabed change. That's everyday survey for 4 months. As we head out, the channels show you exactly the same thing. It's another story, the bed forms, but now we're seeing 7 events total in 4 months. But when you look at the whole system over 17 years, which we have done, the upstream end's changing fast, but watch this channel. It wasn't there, now it's appeared. And now way out on the lobe, we're starting to channelize the lobe. So it's a fascinating location. And what we've been able to do is monitor it, as I say, for 17 years. And it's been primarily bathymetric change. So it's seabed change detection. And we've seen the channel grow, which is of great interest because the channels are actually reservoirs. They're coarse facies, they're coarse sediments, a lot of porosity. And we've seen the lobes skip forward. But even from the beginning, we've seen this unconstrained flow. So it's a wonderful analog of the deep sea that we can start to test better methods to actually take a look and get the monitor and get the character of these flows. And I'm going to focus on this distal section where it transitions. And what we've had here, we've had a mooring for the last 3 years. The anchors are on either side of the channel. And on a long rope, we've got an ADCP that sits what we like to think as safely above the flow. And these difference maps, so we're looking, that's where the channel finishes up here. I hope you can see my mouse. And it spreads out and it goes on for another 2 or 3 kilometers. And look at the velocities. We'll get, in the summertime, we tend to be there, we'll get maybe 1 monster flow. And it's the one that does all the alteration, all the sort of benign low density flows are nice to look at, but they have no impact on the geological record. 6.5 meters a second, 10 meters a second. And the one we'll focus on is 5.5 maybe, but the ADCP got destroyed. So these are really powerful currents. They're dense, they drag everything. And so you want to find another way to monitor them. And the nice channelization. So ADCPs, even the ones that we had no problems with, this is showing you a record. You're looking at about an hour's worth of data. You're looking from where the sensor was down to the seabed 8 meters below, in this case, 10 meters below. Nothing, nothing, nothing. And then the flow hits. And you can see the velocity is 6.5, 10 meters a second. But if you get in really close, you'll find at that moment, the actual main flow only occupies about 6 to 12 minutes. In that time, most of the time, you can't actually see through the flow. It's too dense. And that's a major problem. Having waited for 2 months to catch the flow, to find that you can't actually see the part that's driving it is very disappointing. And why is that? Well, what you're doing is you're above active acoustics, you're pinging, and you have suspended sediments, and a very small percentage normally of that intensity is scattered back to you. So as long as it's low suspended sediment concentration, your volume scattering strength is a pretty good proxy for grams per liter or milligrams per liter, and you still see the seabed. But when the turbidity current comes in, the concentrations go up, and you start to what actually arrives at the seabed is attenuated. You can play games, you can see the seabed's echo is weaker, so you can guess how much it's attenuated. But for most of these flows over about 2.5 meters a second, it's completely attenuated. And it doesn't matter, I've been doing this at 600 and 1200 kilohertz, but you can't do this at 75 kilohertz, and your range resolution is appalling. So it's really frustrating. So there's another approach, and again, I've been trying active sonars. Very proximally, we'd anchor a vessel, 4-point anchor, and image. And we actually use the LEM3, they're 500 kilohertz multi-beams made by Mesotech, lovely systems. And you can look at the flow as it goes by. You can look straight down, and you can wait for the flow to happen. Hopefully it'll arrive in a moment. Come on, don't disappoint me. There we go, there's the flow. Or you can look straight ahead and wait for the flow to come at you. And this was really powerful at the time because we'd never seen a flow actually happen. But the other thing we were acquiring was looking straight down. And take a look at this. This is the flow. That's a school of fish. And you see the bubbles. As soon as the turbidity currents come by, it releases massive amounts of bubbles. But wait for it to come again, and you'll see all of a sudden the water column, there's radial lines. That's actually the turbidity current making a noise. And we saw this in one of the early tests, and we talked to Alex Hay from Dalhousie, who knows much more about grain-to-grain interaction. And he very kindly actually came along and put a sensor on our probe, a passive sensor. So rather than actively image the flow, just listen to it as it goes by. And it all comes down to work that Peter Thorne did back in the 80s, that he actually had a barrel full of sand and gravel, and he rolled it, it was full of water as well, and he listened. And he noticed that depending on whether you're a gravel, a sand, or a silt, the noise it made had a frequency dependence. The gravels were a low frequency, the sands were a higher frequency, and the silts, if you could hear them, were at megahertz. And what he also noticed is the faster he rotated it, or the more mass that was moving, the intensity went up. So the idea, it wasn't for turbidity currents, it was for rivers and shallow tidal seas, that you can listen to bedload sediment transport. The idea was you could get the grain size and the flux. And the principle is there. As it turns out, it only really works for super well salted sediments. If you've got poorly salted and the turbidity current is classically negatively skewed, or maybe positively skewed, a very broad range of grain sizes. So what Matt Hatcher, the student of Alex Hay, did was he was listening between 10 and 200 kilohertz. You'll notice he was listening for noise from gravels through into the sands. And we repeated this in the last couple of years. Initially, though, I just bought the cheap hydrophones, just audible spectrum up to about 20 hertz. But not last year, in 2019, we're listening up to 80 kilohertz. So what did he find? And so they're listening, and this is the head of the flow. Just wait for the flow to go by. Passive hydrophone. What we're looking at is, this is seconds. So that's the head of the flow. Within about 40 seconds, the whole flow passes us. So it's a very, very rapid event. But look at the signal here. This is the spectrum. This is the intensity by frequency band. If you're at low frequency, the intensity rises, but it's not peak at the head, it's peak in the body. Whereas if you go up to a couple of 100 kilohertz, the head is buzzing, and then there's a pause, and then there's a body. And what they also did, they used all the active sonars I was using, but looked at them when there was no other echo, and they were able to look at the noise, and they found the same thing. That is, at 30 kilohertz, the head wasn't terribly noisy, but it was the body that was making the noise. But if you go up to 200, it looks the same as the passive hydrophone. And they even looked at the M3 at 500 kilohertz, and only the head makes a noise. And the inference from this is that the head is fine-grained sand and silt particles banging together, whereas the body is coarser material and potentially bed load transport. But what was particularly interesting in that study is that they were able to infer, through looking at the physics of grain-to-grain particle interaction, that the intensity should be vary with the 7th power of the speed. So an incredibly steep pickup. They see slow flows, don't make a noise. Over about 2 meters a second, all of a sudden you can hear them. And very, very useful. So we wanted to replicate that. In 2018, it's very simple. Loggerhead make these very nice housings. You've got 24 D cells inside there, and the hydrophone is just that. In 2018, we just used the ones for the audible spectrum, 44 kilohertz sampling. But in 2019, we went up to 192 kilohertz sampling. And you just drop them over the side. Don't put them in the channel. Put them off to the side, and with lots of floats, obviously, to get them back. But the idea is don't stand in front of the moving train. And then you just listen. And you don't know anything till you pick it up. And it's a data management problem. Typically, we're down there for about 2 months till we run out of batteries. But remember, we're logging it at about 200 kilohertz, 24 hours a day. Most of these hydrophones, if you're listening for cetaceans, you turn them on for a minute every hour to save the batteries and to save memory. But these turbidity currents can last 40 seconds. So you've got to log it all. And so Monday through to Sunday, for all the weeks. And we found a pattern, very noticeable. First of all, we can always tell when it's raining, 18 kilohertz noise, it's very clean. We have Environment Canada's record. But to store this, we have 4 of these little micro SD cards, 400 gigabyte cards. And so you've got about 1.5 terabytes of noise. It's mainly noise to work through. But let's take a look at a single day. So this is the way I would present it. So that's 24 hours UTC time. We're interested in the tide because the turbidity currents generally go off at low tide. This is the spectrum going 0 up to 20, in this case, 25 hertz. And so it's a classic spectrum plot. And here's the rain, for example. But what you notice, and in local time, at night, it's beautifully quiet. But at dawn, specifically at 7:30 in the morning, when the employees go into Squamish terminals, they turn on their sanders, they turn on their needle guns, and the fjord gets really noisy. And then during the day, all the dinghy sailors go out. And so you'll notice that anthropogenic noise is really dominating. It's very hard to hear it. There is actually a turbidity current in here, but of course that's 24 hours. And then of course, it's a port of Squamish, so hopefully you can hear this. That's one of the big container ships coming in. And even us, we were trying to, with active sonars, steam up and down the channels. You'll notice we're at low tide trying to catch the turbidity current. You can hear us, unfortunately. That's the diesel on the Heron. And so we're contaminating it as well. And funnily enough, on the weekends, Saturday and Sunday, if it's windy, Squamish is the kiteboarding capital of Canada. They might be greenies, but they aren't quiet. And of course, kiteboarders, you can hear them fall in, and you particularly hear their little outboard motors. So hear them fall in. And you'll hear these little zings. A lot of the kiteboarders have hydrofoils on the bottom of them. And so Saturday and Sunday, we can't do anything because they're a navigational hazard and they're actually surprisingly noisy. So it was disappointing in 2018. Remember, these hydrophones are 100 meters underwater, 2 miles away from the port, but we can hear anything, everything. And it's really kind of depressing about how much noise pollution there is in the soundscape. But we do get turbidity currents. So on this particular day, we got a good one. I think it was 10 meter a second one. But you see, unfortunately, it happened just after dawn, before the port opened up. However, within a few minutes of it, somebody came by with an outboard motor. So that is the noise of an outboard motor. That's the turbidity current. Can you tell them apart? Well, if we zoom in on it, they're quite different characteristics, just listening to an outboard motor. And if you look at a spectrum, you've got all these harmonics. And so if you filter it, just high pass filter the spectrum, you can see the harmonics here. Turbidity currents. Now, this is not at the frequencies that Thorne would suggest. Excuse me, I've got to pick up my dog. Would suggest that the should be made, but a very strange noise, a very characteristic noise was there when there were powerful turbidity currents. I'm going to play it for you. And I honestly don't know what that is. I've been looking online. I know about snapping shrimp, but they don't exist in cold northern fjord waters. I think it's bubbles released. I think it's branches being broken. I've got maybe a few hours worth of this recording, but most noticeably in the spectrum, they are transient events. And with the high pass filters, if you do a directional filter, you can very clearly pick out the noise of the turbidity current. But unfortunately, it isn't the noise of the flow. It isn't the one we want to know about, the grain-to-grain interaction. It's a secondary product. So I ran the filter through a couple of months worth of data, and we found a lot of what we think are turbidity currents. But the noise doesn't seem to vary with the flow, with the head, with the body. It was secondary, but at least it makes a noise. So what I want to move on to now is the 29 operation, and where we caught one big flow, and we'd upgraded our hydrophones so they were logging at a higher rate, so we could see up to about 70 or 80 kilohertz. So we're getting into the range of noise that we would expect for coarse sand particles, coarse and medium sand particles, which is the bottom end of the turbidites that get deposited here. This is the flow, and the flow happened on the 14th of June. And this is a survey. This is from the lip of the delta. It started there, it went down the channel. We have 3 hydrophones set up. One where it's an entrenched incised canyon, if you like. One at the transition from, if you like, the sort of levade channel here onto the lobe. And one on the lobe. We've actually got it on a little bit of a platform off to the side. We don't want it to get washed away. And what you're seeing with the dashed yellow line is that one event. We also have 2 ADCPs in place. So we know that between, I can't remember, one day and the other, which is about a 10-day period, nothing else happened until that one flow went by. So you can actually subtract one survey from the other. And this is a difference map, plus or minus 4 meters. You can see that the channels were active, but not the overbank regions. You can see how much of the lobe is active. And you can see these long wavelength, broad bed forms migrating. That's about a 50 centimeter grayscale change, 6 kilometers away. So a very impressive flow. And we know exactly when it happened and nothing else happened. And we've got everything there. So what can we learn about that flow? Well, the ADCPs are what to start with. So we had 2 of them on the conventional, anchored on either side. So the upstream one, we're looking, in all cases, we're going to be looking at 50 minutes. So about 10 or 15 minutes before the flow, and then until it died away. This one caught it. It seems very nicely. Sorry, this is the velocity, the scale, 0 to 2 meters a second. It actually clipped here at the head. And you can see the suspended sediment. That's a volume scattering strength. It's not calibrated, but it's corrected for all the geometry. But notice what happened when the head went by, blind. We got a 3 meters a second off the top of the flow, but we can't see into the flow. You get apparent fast velocities, but actually, as it turns out, the flow's gone by that time. And the downstream one, nothing. You'll notice it's later, but it picked it up, but within 50 seconds, the flow had grabbed the ADCP, dragged it down and buried it. And we thought this would never happen. It turned out this had happened the year before. We couldn't understand why our ADCP sank and then came back to the surface. So what happened, this is the geometry. That's actually the location of it. The flow comes by, even though the ADCP was 15 meters above the seabed, and the flow, most of it was lower than that. There's some sort of suction effect, and it dragged the ADCP down 200 meters downstream and buried it, and it never came back. But we're lucky because in the water column, I assumed someone had stolen it. It tends to happen. If you look at this rather unimpressive looking little echo, this is polypropylene rope on the mooring that is 120 meters underwater. But once you know it, you can pick it up. So you can see the mooring and it's dragged down. You can see the lines, the two anchor lines. And with very low technology, we were able to get it back. We're extremely lucky. But again, the ADCP, it couldn't see into the flow anyway in the first 50 seconds, but we have no idea how long the flow was. So again, a lot of engineering failed. So what I want to sort of focus on now is that same 50 minutes, but we're going to see what was heard by the 3 different hydrophones. So it's always the same scale. I'm showing you, this is the spectrum 0 to 96 kilohertz on that axis, 50 minutes on this axis. And you can see these colored lines, they're 20, 30, 40, 50, 60, 70, 80 kilohertz, just slices, time series. But notice, of course, the man-made noise sources. But we can ignore everything below 20 kilohertz now because we've got higher frequencies. And you'll notice the only thing that shows up at higher frequencies is the turbidity current. So it's really nice, other than you have to log a lot more. If you look at the slices through it, that's actually exactly the same scale. This is at the upper mooring. You can see the ADCP, but you can see it lost information in that critical, it's about 5 minutes. But now look at the shape of these spectrums. They look exactly what Matt Hatcher and Alex Hay got. Their flow was all done in about 40 seconds. I hope you can't hear my dog snoring here. And but in this case, the flow lasted about 15 minutes. And so you can see that leading edge. Now let's jump to the next mooring halfway down. This is just before the channels disappear, the lateral constraints are there. Now you see the same signature, but it's later. Notice it's moved later, and but it has the same sort of character you've seen before. But this is the one where the ADCP got dragged down. And we have no information from the ADCP, but what you'll see is you have a rise in the signal, you've got that head signature, and then you have a sustained level of noise thereafter that varies by frequency. So the spectrum is shifting as the flow goes by and the intensity. This is actually a much better hydrophone. It's designed for these frequency ranges, whereas if you go back to the other one, this one was really only designed to go to 30 kilohertz. But again, you can see that head information, you can see the body, and you can see when it cuts off. And that's based on noise. In other words, grains aren't banging together. Most of that happens while the ADCP is blind. So let's go to the third and the last one. And that's down, it's on that little platform off to the side of the lobe. And you notice now that the noise rises incredibly slowly and then drops away very slowly. And again, the spectrum, nothing else shows up. All the man-made noise sources are below 20 kilohertz, thank God. So you can pick these up very nicely. If we can make sense of these spectrums, the intensity and the slope, the frequency dependence, we can say things about what's actually driving the flow, which remember, of course, high density flows, you've got grain to grain interaction. So what I've done is I've taken the 3 spectrums and I've rotated them 90 degrees. So time, that's actually 10 minutes from here to here. And I've lined them up. Sorry, 0 to 96 kilohertz. That's the upstream hydrophone. This is the midstream hydrophone. That's the downstream hydrophone. And what I've done is I've just taken a slice where I think the highest intensities are. I'm assuming it's where the head passed by. in each case. And so what we're seeing up here is the spectra while the head went by. And these are in dB. I haven't shifted it for calibration, but that's the frequency. We have to remember we can't use less than 20 kilohertz. And also, because of the design of the anti-aliasing filter, there's a roll-off. The Nyquist is up there at 96, so you're rolling off from about 70 kilohertz onwards. So we've really only got a bandwidth of about 50 kilohertz, 20 to 70. And if you look in there, in this central hydrophone, it's tilted. There's a shape to that spectra. This is actually the really good hydrophone. I only bought one of these. I need to buy 2 more. Whereas if you take a look at the other ones, they have a lot of shape, but the reason is it's not the noise, it's the sensitivity of the hydrophones. I bought these cheaper hydrophones, which aren't supposed to work above 30 kilohertz, but the manufacturer says you can try, why not? And you have these secondary resonant peaks. If you look, you'll see these peaks, and you can see, sorry, dog issues. You'll see in the spectra that you've got these bright zones running through the spectra. They aren't real, they're purely a response of the hydrophone. I could try and gain that up, but unfortunately the noise comes with it. So what you can do though is pick the peaks and look at the relative slope of that spectra. Now let's go from the head to the body, and you'll notice a significant, not just a change in noise level, but spectral slope. And so this is something we believe is going to be very good for actually identifying what's going on. And so I kind of want to finish with a model I've been trying to develop of what you would hear if you're a hydrophone and the turbidity current goes by. And I kind of think of it as the passing train analogy. Imagine you're sitting on the side of a hillside and a locomotive comes by. You hear it in the distance, it gets louder as it comes towards you, and it gets quieter as it goes away. We'll assume for now the noise source is point, it's just the locomotive. So it rolls by. So as this is actually the topography, that's the turbidity current head coming by past our 3 hydrophones. So for hydrophone B, you should see the intensity rise up, and it's controlled, of course, by the range, 1/r squared, and the attenuation at the frequency you're looking at. So you'll notice the red is actually the 20 kilohertz. Listening to the same noise at 80 kilohertz, the rise up is much steeper. It's the same spherical spreading, but there's much higher attenuation. So you get to the peak and you go down. So you get a very good peak in intensity, which tells you when the noisiest thing's going by. So if you have a whole bunch of them, you get some velocities. You can check that because you can look at that slope at different frequencies. You know the attenuation as a function of frequency. So let's actually try and do that for the real data. So I know where they are. I know in terms of kilometers down the channel, I've measured it, and I've surveyed each one in with water column and exactly how high they are off the seabed. And I know it took 4.5 minutes to go from A to B and 7.5 from B to C, and we had kind of nice ways to align the clock with random noise sources. Once you know speeds, all we know is the average speed between A and B and B to C. So between A and B, a lack of any other knowledge, I'm going to assume it goes at a constant velocity. I know before A, it had to have a standing start. So I'm going to assume linear acceleration. Between B and C, I'm going to say it linearly decelerates at a rate at which will occupy 7.38 minutes, and then I'll let it slow down. Now I can convert it into a time plot. I know the time. And then what I can do, if it was just a single point source moving down of the same intensity, I can say when I should hear it, how the echo should rise up, not the echo, the radiated noise, and die down. Of course, the real data doesn't look like now. I've got the 3 profiles from the 3 different moorings there. Let's just look at one of them. And we're looking at the 20 kilohertz, 40, 60, and 80 kilohertz time series. You'll notice the main thing is they don't look like, they actually look like on arrival, you can see the rising signal, that's the head, but it doesn't drop down again. Clearly, I'm not modeling the body there. Also, if you look very carefully, you'll notice the 20 kilohertz rises much more rapidly than this, which is a constant velocity model would assume. Now let's jump to the middle hydrophone. The middle hydrophone, now you'll notice again it's lopsided. The rise actually matches very nicely the constant velocity model here, but now you've got a much longer body signal. Let's finally go to the last hydrophone out on the lobe, and you'll notice the rise is incredibly slow. It's actually much slower than would be predicted if it was coming past at a constant velocity. That's what's assumed in the third plot. And then it drops away, but unlike the previous ones, it doesn't drop away and have a step function. So what we've got to do is add a body to our turbidity current. So we've got a head with its head speed. We've already said we know what noise it's going to make. Notice the noise varies with its velocity to the 7th power, according to Hatcher and Hay. Now I'm going to add a body. And the body is a series of radiating noise sources. And I get to choose their intensity. They're all radiating according to their velocity to the 7th power. But if I'm listening at this point, I hear the head at that range. Each one of the bodies I hear at different ranges. So what I have to do, so the total intensity is intensity of the head plus, it's all incoherently added, the sum of all the different intensities of the bodies. But remember, each part is at different ranges. Now, remember I mentioned that there was that flow stretching phenomena, and that's something was seen at Squamish. So I can choose the velocity of the body. And what I'm going to do is I'm going to say the body progressively moves slower than the head. And it moves at a speed of the head, not the head now, but the head when it was at that location. And so what I can do in the model is I can stretch the flow. So it's up to me how much I want to stretch the flow. The only constraint is I have to fit the observations. And of course, the flow isn't finite, it's a bunch of them. So what I've got to do is I've got to tune this. I've got to let it go, run down, and reproduce the signal that I'm seeing. And what you'll notice, of course, is because I'm allowing it to stretch, the body gets longer and longer with time. But then a funny thing happens. When you get out on the lobe, the head slows down, but the body is still back in the channel, and it kind of collapses again. And so I can control that. And so I can decide that, and I basically tune it. It has to fit this. And so what you see is each one of these, I can model the rise time. And remember, this one was too steep. This one was too shallow. To be too steep, you can explain that by the flow accelerating towards you. Remember, it starts off, it's quiet because it's the noise it's radiating depends on its speed. So it catches up on you. So I can actually predict accelerating flow. Whereas out on the lobe, I actually know the flow is decelerating. It's like a bunch of drunks coming home after the pub. Shh, be quiet. And you get quieter as you get there because the velocity is dropping. But the thing I've got to fit is the body. And you can see very clearly for the first two that you've got this break in slope. You've got an intensity that's dropping away, and then you've got a break in slope, and it drops away steeper. But when you get onto the lobe, it isn't that. So what I'm going to do is I'm going to try, and I'm still in the process of doing this, but I built the model at least. I've got A, B, and C. And what I do is I basically let the flow go downhill, and I listen at each one of them, and I build a synthetic time series, and I can build it for all the frequencies because I've got all the attenuation coefficients, and I can tune it until it fits those. So you can invert with care. It's kind of interesting to realize how long these flows are. So it starts, goes under A, going towards B, and it's now under B. But notice that A is still hearing it. So I've got it here, B, the head is past it, and you're still hearing it A. It's almost arrived at C, and the tail is still there at A. So you can see how long these flows are. They're about 3 kilometers long. And then actually, I'm not quite sure what to do because I've modeled it as a singular path, but from the depth differences, I actually know that there's 3 paths. And I'm not quite sure how to handle that because I've been assuming a unit area width of a channel that's radiating. If that width increases, how do you handle that? So I'm not quite sure how to handle that, but if I had more hydrophones, I'd be able to solve for that. And so I'll finish. In conclusion, it is a work in progress, but the great thing about hydrophones is you can go where ADCPs fear to tread. And these time series and spectra allow us to get away from the anthropogenic contamination, which I didn't even realize. We can look at the change in spectral response between the head and the body, and it's not the same at all the different locations. So the character of the grain-to-grain interaction is changing. I can recognize heads and bodies and changing, and I can recognize accelerating and decelerating. So that's exciting potentially. But we need to do it again because I got it wrong. We need to switch to all broadband hydrophones. We should calibrate those hydrophones. I'd like to put more ADCP back because I still need to know what's actually happening, even if it's imperfect. I want to add more hydrophones, of course. So not 3, 6, 10, they're cheap. They're only like 5 or 6K a piece. Observe more flows. And now that COVID's finished, I hope we'll do that. Keep on mapping. And the last thing is I love the model because it's basically, I feel like a child playing with a train set. And so I'll leave it at that point. If there are any questions, it's very much a work in progress.
Thank you, Professor Hughes Clarke. That was a really excellent presentation. If anyone has any questions, feel free to either type it into the chat and I can read it aloud for you, or you can unmute yourself and ask it directly.
I have a question.
Go ahead.
This is Larry Ward, John. John, when the turbidity current elongates, is it diluting the sediment load, or is it eroding and picking up sediment as it goes along and transporting a bigger load?
It's that's the million-dollar question: is it igniting or not? And it's this. There are models. Gary Parker has generally the best ones. He tends to layer average if he can, but we don't know. But what's amazing with the Congo is these flows, the head is running away from the body, but the body can maintain itself. So it must be maintaining that sediment load. We don't know. And there's a whole group of people involved in this. There are modelers and there are observationalists, obviously, like myself. And but we should be able, if we can see a body pass, we can listen to the body and we can see, is the intensity increasing or decreasing? That tells us potentially how much is in suspension. That might be a little bit too optimistic. I would like to say we can get the grain size, but one of the conclusions, particularly of Matt Hatcher and Alex Hay, was the spectra were flat, and it's when real grain sizes are not that well sorted. But we don't know. But this potentially, if we have enough of these and we instrument more active flows, maybe we can get there.
That's fascinating. Fascinating.
Okay, I have a question from Gabriel Venegas. Very interesting talk. Thank you. Could the snapping sounds be due to the released bubbles cavitating in the turbulent flow? Could you see bubbles on the active sonar during that particular event?
I don't know. I don't think the bubble would cavitate on its own. They release. We can see them releasing with the active sonar. I almost want a video camera, except I couldn't store 2 months of video, to have a look, because is this something that's 50 meters away, or is, as you're suggesting, bubbles coming up and actually hitting the hydrophone? They're upside down, so the hydrophone's pointed down. Or are they little euphorsids that are snapping them? I don't know. I'm real curious. Does someone recognize that noise, or maybe we should find out what it is?
John, this is Gabe. Yeah, I was kind of, that sounded to me like a cavitating bubble. So that I was thinking that maybe once the bubbles got resuspended in the turbidity current, there was enough turbulence in the flow that there's a sufficient negative pressure to cavitate the bubble in the turbulent flow. That was just my thought, but I was curious.
I mean, this is what's great, as a group of you working in bubbles, to maybe make sense of this. I mean, by all means, look at the spectra of this, but I'm very curious. There's certainly massive release. I don't know a lot about their sizes. I've been imaging them, but with narrowband sonars, because you can't tell a lot.
Neat, thank you.
Jose kind of says mussels produce a similar sound as well. Don't know if there are any in Canada though.
Mussels. Well, it could be biological, and if there are mussels. I don't think there's mussels, but there's all sorts of shrimp down there. I imagine any infauna would not like a turbidity current. So this, and if there are little bivalves, they would snap shut because it's a pretty hostile environment. This may be a biological signal.
Great, thank you. Are there any other questions?
Yeah, I've got a question. Hi, John. Nice to see all
Brandon.
the Squamish bathymetry again. In your train model, that's a pretty interesting idea you've got there. Are you specifying like the number of cars in your train, or are you letting the data kind of figure that out?
Other than I end up making it a continuum, I haven't decided. I started off making it discrete, and then you can kind of integrate continuously. But it actually comes back to Larry Ward's question. If the flow stretches, do you conserve noise per unit volume? And I'm not sure what to do with that. So at the moment, it started off being a N of them, but then as you listen, you'd hear each, it's like you could hear each carriage go by. You know, once the locomotive's gone by, you hear the clickety clack of the wheels. It should be continuous.
Okay, cool. Nice model. Thanks.
So John, this is Jack Dill. I was wondering if you wanted, could you use this passive approach at some of these bigger canyons where the events are much less frequent? And I mean, could you handle sampling at that rate for a year in order to get one event? I mean, what would you do with all that noise data for a year deployment?
It would be a horrible amount of data. It's interesting on the in Butte, they put one icy listen down, and on Congo, they're recording at completely the other end of the spectrum. They put basically seismic recording because they think they'll hear a rumble down below a couple of hundred hertz. But if you wanted to record 200 kilohertz for a year, well, actually, I think there's now a terabyte micro SD disk. It's I think we just wait. But there's certainly less battery involved. We're starting to get enough memory. The other thing is, now that I've logged all the wave files, you don't need to keep them. You could collapse them, just save the spectra. You could downsample. But it would still be cheaper. You saw the moorings they put down for Congo. They're millions of dollars. You could put 100 hydrophones down there, even if you only got half of them back. So I think we need to understand what we're listening to. And I think we'll do that in the shallower fjords. But yes, I agree. I think long-term, we can monitor these even rarer events, but it is a data volume and, as always, a battery issue.
Great. Thank you again, Professor Hughes-Clarke, for presenting, especially with the last minute notice. It was really excellent. And thank you everyone for joining. I want to mention that next week we have Dr. Dawn Wright from Esri speaking. So be sure to look out for the emails for that next week. And everyone have a great, fun, and safe weekend.
And get registered if you're not.
Yes.